Greetings, salutations, all those nice things. Welcome one and all to part 3 of trig identities. And this is where we are looking at sum, difference, and double angle identities. Statements that are true when we look at a sum of angles, so one angle plus another, a difference of angles, so one angle minus another, and a double angle, and that's an angle plus itself, or 2 times that angle. There are some identities listed on your formula sheet. It's these ones down here. But what we're noting there is sine of alpha plus beta. We don't just have sine distribute. We're not going to get just sine alpha plus sine beta. And if you try doing that on like a test or quiz or the provincial exam, you're not going to get any of the marbles. And it's going to be very, very sad. Super key that we recognize this as having a substitute listed on the formula sheet. And that's the way we're going to apply it. So again, sine of alpha plus beta is not equal to sine alpha plus sine beta. Also, apologies for putting an A instead of alpha there. That was supposed to be alpha the whole time. These three are the sum identities for the primary trigonometric ratios for sine, cos, and tan. And again, no distributing. Use these formulas. Use these formulas. We don't directly have the sum identities for these secondary trig functions, but if you needed something, you had cosecant of alpha plus beta, I would just find the sine of alpha plus beta, and then take the reciprocal. Or same for secant, use cosine, and then take the reciprocal. For cotangent, take tangent, find the reciprocal. Now again, there are 2 other types of identities that we're going to look at in this lesson. These are the sum identities. They all involve addition. We're also going to get the difference identities and the double angle identities, and we're going to base them off of these 3. They are on your formula sheet already, so sure, you could argue that we don't really need to discover them or prove them, but it is very highly important that you understand where they come from and not just blindly use them because Mr. Authority, the A in Mr. A is obviously for authority, told you to just use these formulas. They come from somewhere. There's a way to verify, prove that they are legitimate. And aside from taking these ones for granted, we're going to say that based on these, there's ways to prove that the other ones are legitimate. Having said that, there are ways to prove that all these exist. I think there might be 1 or 2 in the practice work. Who knows? Anyways, we are going to prove something for sine of alpha minus beta. We're going to get a formula for that. It should look same as the one on the formula sheet. Same for cosine of alpha minus beta. We'll get something for tan of alpha minus beta. But it does require us to note something about these graphs. Here's a graph of cosine. This graph has reflective symmetry. That is, if we flipped it over the y-axis, reflected it horizontally, we'd get the exact same function back. To take f of x and reflect it over the y-axis, to reflect it horizontally, we'd be looking at f of negative x. And we're saying that when we do that, we get the same thing back. So here's that statement. When you take cosine and reflect it over the y-axis, you just get cosine itself right back. So that'll be a key for us to use. Additionally, you take a look at sine. Here's your sine function. It's got rotational symmetry. So if we just reflect it, we're not getting the exact same thing back. You'd have to take a segment and then rotate it 180 degrees to get the other. So there's your rotational symmetry in play. But another way to rotate something by 180 degrees is to first actually flip it either horizontally or vertically, and then flip it the other way. So that is, we need to reflect it about the y-axis, and we need to reflect it about the x-axis. And if you take f of x, you want to reflect it both ways, well, you'll have to take f of negative x to reflect it horizontally, and then apply a negative 1 outside to reflect it vertically. Put into action for this sine function, we have this statement. So you take the sine function, reflect it horizontally, and reflect it vertically, you just get the exact same graph right back. And if you multiply both sides by -1, you get this statement right here, that sine of negative x is equal to negative sine x. We could also show this for the tan function. Tan has the same rotational symmetry as the sine function, so likewise, we can make this declaration. Tan of negative x is equal to negative tan of x. So those are going to get used in our development of the difference identities. When we look at the difference identities, we look at something like alpha minus beta with sine applying to it. It's worth noting we can phrase that as a sum. To subtract something is just to add its opposite. So we are going to phrase this as the sine of alpha plus negative beta. From here, we are going to use the sum identity. And the sum identity says if you're taking the sine of a first angle plus a second angle, well, it's sine of the first, cos of the second, plus cos of the first, sine of the second. And in this case, alpha is our first, negative beta is our second. So that's what's going to go in for each of these angles. That allows us to say then that this is sine of alpha times cos of negative beta plus cos of alpha times sine of negative beta. It's a huge key critical step. I mean, they both really are. The ability to phrase subtraction as addition allows us to use the tool that we have, the sum identity. And then we can use that sum identity. We plug things in, and we get this result. It's not as neat and tidy as the one on the formula sheet yet, but we're going to use those properties we found. So we know that if we take cosine and reflect it horizontally, we get the same thing back. Again, that was saying that cosine of negative x is the same thing as cosine of x. So this cosine of negative beta is the same thing as cosine of beta. We can write this then as sine alpha cos beta. We also here have sine of negative beta, and we established that if you take sine of negative x, that's the same thing as negative sine x. So this whole thing right here is negative sine of beta. And that negative can just go right out in front. So minus cos alpha sine beta. And this is the difference identity for the sine function that you'll find on your formula sheet. I super dare you right now, double dare you? Sure, why not? To try getting these other two. To try getting cosine of alpha minus beta, try getting tan of alpha minus beta. And spend a solid 5 minutes on it before resuming this video. Give it an honest, earnest effort. And consult with those around you, see what you get, then play this. You can pause now. Under the assumption that you paused and have now resumed the video, let's take a look at cosine of alpha minus beta. As with sine, we're going to phrase that subtraction as addition of an opposite. When we consider the cosine function, or the sum identity for cosine, cosine of angle 1 plus angle 2 is cosine of 1 cosine of 2 minus sine of 1 sine of 2. Mostly certain I got that correct. I don't know. Let's just double check. Oh, thank goodness. So first thing, second thing, first thing, second thing. And I am phrasing it that way with the 1s and the 2s just to wrap my head more around alphas and betas. Since I'm turning this negative beta, it's taking the place of the beta in the identity. There's too many betas swimming around here. But now I can sub this in. So it's cos of the first thing, cos of the second thing. Cos of alpha, cos of negative beta. Minus sine of the first thing, so sine of alpha, sine of the second thing, sine of negative beta. And again, we are using those other statements we declared to be true. Cosine of beta, or of negative beta, is the same thing as cosine of beta, so this is cos alpha cos beta. Sine of negative beta was negative sine of beta. So negative times that negative is going to give us a plus sign in the middle. Sine alpha, sine beta. And now this one is du and done. This is something you will find on your formula sheet as well. And let's check out tan. Tan of alpha minus beta is tan of alpha plus negative beta. And that formula sheet has a fraction on it. Oh, do I remember that off the top of my head? I think it's tan. Oh, let me write it out here somewhere. Tan of first thing plus second thing. Pretty sure you add them on top. Tan of first thing plus tan of second thing over 1. Is it plus? Guess we'll find out in a second when I check it. Who knows? Oh, so close. Should have been 1 minus. Good thing that formula sheet exists. Not gonna lie, when I had to find tan ratios of sums and differences back in the day, I had to memorize these formulas, which kind of sucked, but also I didn't memorize this one. I just took sine divided by cosine and was done with it. In my head, that was way easier. Regardless, though, we do have the formula sheet, so we'll just sub things in based on that. 1 minus tan alpha tan negative beta. And tan has the rotational symmetry. Tan of negative beta is negative tan of beta. So with that substitution in, we get tan alpha minus tan beta over 1 plus tan alpha tan beta. Again, that is something on your formula sheet. Don't have to memorize it, but here's where it comes from. And those are your 3 angle or 3 difference identities for sine, cos, and tan. And if you need cosecant of alpha minus beta, I would start by getting sine and then taking the reciprocal. You need cotan of alpha minus beta, I would start with tan, take the reciprocal. There are also double angle identities. A double angle is of this kind of form. It's 2 alpha. And we can express that as a sum as well, because 2 of something is that thing plus itself. So when we look at something like sine of 2 alpha, we're going to first phrase that as sine of alpha plus alpha. Now again, the sum identity for sine says that sine of 1 plus 2 is sine of the first, cos of the second, plus cos of the first sine of the second. It's just the first and second are the exact same thing in this case. So when we sub it in, we get sine of the first thing, cos of the second thing, plus cos of the first thing, sine of the second thing. This is pretty close to being done. It's not quite what you see on the formula sheet, but we can note that these two terms are actually the same. Noting that the order that you multiply two things in doesn't matter, like 3 times 4 is the same as 4 times 3. You could say that cosine of alpha times sine of alpha is the exact same thing as sine alpha times cos alpha. So you could consider that, or at least in our head brains, that's what we're thinking. Because then we can note, hey, we've got two of the exact same thing being added together. So that is just 2 of that particular thing. And again, now we're at a result that is on your formula sheet. Sine of 2 alpha is 2 sine alpha cos alpha. At this point, try getting double angle identities for cosine and tan. And oh, there's cosine. Thought we lost it. We're safe. It's cos to us. So take, again, a solid 5 minutes to honestly and earnestly give this a solid go. Like, really engage in it, see what you get, discuss with those around you. Pause the video when you do so, and resume again after 5 whole minutes. So pause now. Hey, it looks like you're back. Did you give it an honest, earnest effort? I sure hope so, because now we're going to see if you get the same as what I get. Cosine of 2 alpha is cosine of alpha plus alpha. And if we are considering that cos of alpha plus beta is pretty much cos minus sine, here we're going to have cos minus sine. We put our first angle in these places. We put our second angle in these places, but they're the exact same angle, so it didn't really make any difference. Only thing left from here is to say, hey, we've got cos of something times itself. You multiply something by itself, that's squaring it. And same, sine of something times itself, that's just taking sine alpha and squaring it. So boom diada, there's this. That's on your formula sheet as well. Cos of 2 alpha is cos squared alpha minus sine squared alpha. Lastly, tan of 2 alpha. That's for sure in my head brain for what its identity is. But let's start with that. Tan of alpha plus alpha. And as I recall, it's tan alpha plus tan alpha over 1 minus, for sure, minus tan alpha, which gets us a result of, well, top is something plus itself, so that's 2 of that thing. Bottom, we have 1 minus something times itself, so that's 1 minus tan squared alpha. And this is on your formula sheet too. So there are some identities for sine, cos, and tan of 2 alpha. You will note on your formula sheet there are actually 3 options given for this one, for cosine of 2 alpha. This is one of them. There are 2 others. And those 2 others are based on the fact that we're seeing a cos squared and a sine squared. There's difference between them, not addition. But we do know that if we had cos squared of theta plus sine squared of theta, we would get 1. And that correspondingly means things like, well, cos squared of theta is 1 minus sine squared of theta. So when we consider that dividing line, we can say that while cos of 2 alpha, 2 alpha, is cos squared alpha minus sine squared alpha. Honestly, I really don't like that writing. I'm just going to redo it. Cos of 2 alpha is cos squared alpha minus sine squared alpha. We can take this cos squared and replace it with 1 minus sine squared. Simplifying that, you could say we can open up the brackets. We'll definitely have that 1. We'll subtract sine squared. We'll subtract sine squared again. So really, we're subtracting 2 of sine squared alpha. And similarly for the other one, starting with the identity on this page above, again, cosine of 2 alpha is cos squared alpha minus sine squared alpha. We can replace sine squared of alpha with 1 minus cos squared of alpha. And opening up those brackets, we've got negative of something. It distributes to both. So we've got cos squared alpha minus 1 plus cos squared alpha, which is overall 2 cos squared alpha minus 1. And that's the last of those identities. Again, a whole bunch of stuff that is on your formula sheet. So recapping, we have these sum identities for sine, cos, and tan of alpha plus beta. We have difference identities for sine, cos, and tan of alpha minus beta. So these, again, on your formula sheet. And lastly, we have the double angle identities for sine, cos, and tan of 2 alpha, where each of these plus the bonus 2 at the bottom are all on your formula sheet. We're going to be looking at examples that kind of match some of these cases. We have to be able to identify what it most closely resembles on that formula sheet and link it to the other side of that equals sign. So taking a look at this, like checking it out, it says write it as a single trig function. We're not going to evaluate it, but we can write it as a single trig function. What we can recognize here is this is cos alpha cos beta plus sine alpha times sine beta. And if we look at what that most closely resembles on the formula sheet, I mean, that is, let's just scroll up to where it is. It's this. Cos, cos plus sine, sine. And that ties to the difference identity for cosine. Did I just screw that up entirely? Is cosine, cosine? No, it's cos plus sine, sine. Nice. And again, that ties to cosine of alpha minus beta, which means that this is actually straight up cosine of, there's our alpha at 72 degrees, minus beta, which is 49 degrees. So it's seeing what replaced what, and making that tie, seeing what this looks most like, and then making the substitution. Of course, I'm going to close off that bracket to avoid the E4 brackets error. It has been written as a single trig function. We don't have to evaluate, but for best form, we should be actually performing the subtraction step itself, 72 minus 49 for whatever that value is. I don't know, 23? And then this one is DUN, done. I double dare you? Triple dare you? Goodness. Triple dare you to try the other three examples. Again, taking a look at whatever we're starting with because it resembles something on the formula sheet. Hey, look, this one's already just straight up in there. That's kind of neat. We'll figure it out. So it resembles something on the formula sheet. So sub it into whatever it is it resembles. Then plug it into the other side of that equal sign and evaluate. Again, gives us another solid 5 whole minutes. And then once you have done so, after you've paused, given it 5 minutes, really tried this, given it an honest effort, then resume the video and let's check your answers. You can pause now. Welcome back. Let's do this. This is 2 sine alpha cos alpha. And that's the formula for sine of 2 alpha, which means that this is sine of 2 times 5 pi over 12. That is sine of 5 pi over 6. Perfect. We could evaluate that. Question instructions said not to evaluate, so I guess we won't. But we could. But we won't. But we could. But we won't. These ones we will evaluate. And again, drawing the links, this is sine alpha cos beta plus sine beta cos alpha, where beta is 7 pi over 12 and alpha is 1 pi over 12. Sine cos plus sine cos, that is the formula for sine of alpha plus beta. So I'm going to rephrase this as sine of alpha, which is pi over 12, plus beta, which is 7 pi over 12. Adding those up, we could take this in lots of steps, sure. Pi over 12 plus 7 pi over 12, that's 8 pi over 12. Not sure how to evaluate it? That's okay. We can reduce the 8 over 12. 8 over 12 is 2 over 3. And we can evaluate sine of 2 pi over 3. If you need to reference your unit circle or you want to go special triangles and cast rule up in this business, we got a 1, 2, root 3, all that jazz. Pi over 6 opens to the 1 because it's smaller than having a third of a pi. And with that, we know it's related to, so opposite over hypotenuse. It's going to look like, wrong color. Root 3 over 2. And then just don't forget cast rule. This angle's in quadrant 2, where sine is positive, so this one is done. Done, done, done. Last up, cosine of some difference of angles. Again, if you were to take this and say that it's, okay, that's a highlighter, pointer. If you were to say that it's cos of pi over 3 minus cos of pi over 4, you're going to have a hard time getting marks for this question. Because again, these functions don't distribute. You have that formula sheet for a reason. Please, pretty please, use that formula sheet. So that formula sheet says cosine of alpha minus beta is cos alpha cos beta plus sine alpha sine beta. In this case, then, that's cosine of pi over 3 times cosine of pi over 4 plus sine of pi over 3 times sine of pi over 4. And we can evaluate each of those one at a time. Cosine of pi over 3 is 1/2. Cosine of pi over 4, you could phrase it a couple ways. I tend to go root 2 over 2, but if you said it's 1 over root 2, that's also a-okay. Sine of pi over 3 is root 3 over 2. Sine of pi over 4 is root 2 over 2. And again, same. You could phrase that as 1 over root 2, and that would be okay. It'll change what our final answer looks like, but again, multiple options for how it looks. Turning this into a single fraction, you can do it in one step or take a couple. You've got root 2 over 4 plus root 6 over 4. And overall, that is root 2 plus root 6 over 4. And this one is DUN done. If you had phrased these root 2 over 2's as 1 over root 2, the answer would look ever so slightly different. You would essentially have 1 plus root 3 all over 2 root 2. Both are totally okay. You are allowed to, for trigonometry purposes, have radicals in your denominator. Actually, really for any purpose in this entire course. You can have square roots in your denominator. That'll be fine. Just leave it in that unrationalized denominator form and move on to the next question. Are there any questions, comments, or concerns? Well, I don't see any, so give yourself a way high five. And then move on to some practice work. If you want to open a textbook, I suppose you can, but I would more so just focus on this additional practice. I almost revealed the spoilers there. That would have been embarrassing. You don't want to see that yet. So give that a go, give it a spin, give it a shot, give it a whirl, give it a stab, give it a try, give it an attempt. And I will see you in the future. The end. Or is it the beginning? Did I not